Okay, so I just wanted to make a quick video summarizing binary adders because there are some very good questions in class about how these things work and how we're going to combine multiple digits. So let's go through the whole picture. So our goal is to add two numbers, say 101 and 111, with a circuit. And we're going to build up on this. But first of all, what should this sum actually be? If we just look at what we do for normal decimal numbers, for example, 27 plus 94, well, we just add the individual columns normally. So the 7 plus 4 gives us 11. We carry the 1. 9 plus 2 also gives us 11. And that gives us 121 because we've had this carry. We've carried that power of 10. The exact same algorithm works for binary. 1 plus 1, well, it's going to give us 2, binary for 1, 0. So we carry over a 1. 1 plus 1 as well will give us a 0. So now we have 1 plus 1, which is 1, 0 in binary, plus 1 for the carry will give us 1, 1. And we can make sure that this adds up. Let's check. 1, 0, 1 in binary is 5. And this is 4 plus 2 plus 1, which is 7. And this is 8 plus 4 plus 2 plus 0 plus 0. And that's going to give us 12. So this actually does work in the exact same way that it would for decimal. So from this example, there's 2 points that are very pertinent. Is 1, we need for adding two, say, 2-digit numbers, we're going to need 3 digits to store it. Or adding n-digit numbers, we need n plus 1 digits to store it. 2, we need to keep track of the carryover of digits. So let's build a circuit which does this. So notice that when we're doing even normal arithmetic, we concentrate on one column at a time and perform that addition. And then we move on to the next column, keeping track of any carryover. So we do the same thing with binary. Let's add two numbers, A and B. And we can build this up exactly like a truth table of any other logical elements. So we have AB. We'll look at the sum in decimal. 0, 1, 1, and 2. And the corresponding sum in binary, which is going to be 0, 1, 1, and 1, 0. And this is that problem that we had before where we had to keep track of a carryover extra decimal place. And the way to do that with a circuit is we just keep track of a carry bit. We'll have 2 bits of an output when we're adding two 1-bit numbers and the original sum. So here carry is going to be 0 and 0, 0 and 1, 0 and 1. And when we add 1 plus 1, we're going to get 1, 0, 1 carry, and 0 in the sum column. And we can look at these truth tables independently. We can say that this is none other than an exclusive OR. And this is just an AND gate. So we can combine these two in a circuit. We're going to have an A and a B. These are the numbers we're adding. And we can literally put them into a XOR gate and call that our sum. And just tap these both down into an AND gate and call that our carry. We can wrap this whole thing into a black box and just call it a binary half adder. 2 inputs, A and B, 2 outputs, sum and carry. Now you might wonder why it's called a half adder. Well, if this works 100% of the time for our first column, our first digits in our binary addition, but the second, our value may have been different if we had a carryover bit from the previous addition. So in order to take that into account, we need to add a third input, a carryover input. And making a circuit which does that is called a binary full adder. So let's move on to that circuit. We'll have 3 inputs, like we said, A and B, and then a carryover, which is from our previous addition. Now, all we do now is we've already figured out how a binary half adder works, and we put it in a box, and don't worry about its guts anymore. We put the sum of that into a second binary half adder, and this is that these layers of abstraction that we talk about in class. And that's going to go out here. We're going to keep track of this carry. We'll tap it out, and we'll put the input carry to the secondary binary half adder. This is going to go out to our sum, and we're going to take the carry from this one, just put it to a standard OR gate, and that'll be the carry out from our binary half adder. And this makes a binary full adder. So how should a binary full adder work? Well, let's first of all write this as its own abstract unit. C in, they're going to have sum and carry out. And we can now use this, tap it out to its own set circuits, and use it just as a individual unit on its own. Okay, so what should this binary full adder actually do? Well, the first thing to note is we have 3 inputs, so our corresponding truth table is going to have twice as many entries. But we'll notice that in the case that the carry bit is 0, this whole thing is going to reduce to a binary half adder, right? Because if this is 0 here, this input will become a 0, and we'll have A and B just going into the first binary half adder. Because this carry bit is 0 into the second binary half adder, and because the truth table for the carry is an AND gate, the carry of this second binary half adder is always going to be 0. So we'll have a 0 to this OR, and what this thing carry is going to put out in the total end is going to be just the carry of the first binary half adder. So it's just going to pass that through. Similarly, since we have a 0 to this part, the output sum is going to be whatever we put in to the sum from A and B. So this is going to be exactly the same as our binary half adder. Namely 0, 0, 0, 1, 0, whoops. I put these backwards. I'm going to swap them around for just for continuity. Now what about the other case, in which case we do have a carry bit? Well, in this case, we can work out a few examples. First of all, if A and B are both 0, the output of the binary half adder is 0. So the sum is going to be 0 plus 1. It's going to give us a sum of 1 and a carry of 0. How about in the case that A is 1 and B is 0? or vice versa. Let's just mark that with little asterisks, and we'll try to work out what happens in that case. Well, 1 plus 0 from this binary half adder is going to give us a sum of 1 and a carry of 0. But this 1 here is going to give us a sum of 0 and a carry of 1. So that sum is going to go to 0, 1 because of the OR gate. And it'll give us this 1, 0, which is binary for 2. In other words, 1 plus that 1 from the carry. Since A and B being 0 and 1 is completely symmetric with 1 and 0, we have the exact same thing for this column. And the other only case of interest, we'll put a little green asterisk here, is when A, B, and carry are all 1. Then we have the first binary half adder putting out 0 and 1. And that carry is going to be a 1. So this is going to give us 1, 0. And this will give us a 1 here and a 1 here. So we can look at this, the decimal representation of these. It's going to be 0, 1, 1, 2, 1, 2, 2, 3. So the second column is just 1 plus that first 4 there. Not really a column, I suppose. And that's how a binary full adder works. Now again, once we've done that, we can encapsulate it into this box and call it just our binary full adder. So finally, how do we use these binary half adders and full adders that we've just created to actually perform n-bit addition? Looks like we're running out of real estate here. So I'm just going to change our page size to auto. And I'm sure there's a better way of doing this, but I'm inept at using this program. So our goal now is to add 2 1-bit numbers. So for example, we want to add 101 plus, let's use a different one, 110 to make it interesting. So if we want to add those, we can represent a binary number as, this would be A0, A1, and A2. This is a 3-bit binary number. And this here would be B0, B1. We need to use 3 bits to specify this number. And that's going to map to four sum numbers. So sum 0, sum 1, sum 2, and sum 3. Remember, because we need to store 2 3-bit numbers. The sum of them becomes a 4-bit number in general. So how are we going to do that? Well, we just take our things that we've already created and wire them up together. So let's look at that potential circuit that we'll make. Our first digit, we're just going to need a binary half adder because there's no possible way we're going to carry in a bit. We could have a binary full adder and just set the carry to 0. We'll have a binary full adder here. We'll give it some inputs and outputs. And another one. A, B, C, sum, and carry. And this half adder will just have A and B. So let's see how we want to wire this together. Let's just look at how we're actually going to do it. How would we do it if we're not using a circuit? If we're using just binary numbers and pen and paper? Well, we'd first do the first column, which is 1 plus 0. So I'll wire in A0 and B0 directly into A and B here. And this output of that is going to be the 0th digit of our sum. The carry, we're going to wire directly into the carry of the other bit. And in here, we'll put our second 2 bits, A1 and B1. Those will get wired directly into A and B. And the sum of that is going to be our first output sum. We'll have our final bits from our 3-bit binary number going in here. Again, we're wiring the carry in. And that's going to have a sum, which will be our second sum bit. And finally, the carry will carry our 3rd bit if necessary. And this is a 3-bit binary adder. We're combining things we've already built to make something useful that works on a bigger level, just like we've combined in class silicon to make transistors, transistors to make these logic gates to make binary half and full adders. We're combining binary half and full adders to make a n-bit summing circuit. And this is it, but we better check to make sure that this works. This is our 3-bit adder. So let's make sure this binary adder does exactly what it should. So for the first 2 bits, we have A0 and B0, which are respectively 1 and 0. That goes to a sum we know of 1 and a carry of 0. The second bit, A1, is going to be 0, and B1 is 1. So that will give us a sum again of 1 and a carry of 0. A2 is 1, B2 is 1. So now we have 1 plus 1, which will give us 0 and a carry of 1. So if this thing works as it should, S0 is 1, S1 is 1, S2 is 0, S3 is 1. Let's verify that. So the sum 101 gives us 4 plus 0 plus 1, which is 5, plus 6, that gives us 11. And this is 1 plus 2 plus 8, which is 11. So yes, this circuit works. We've now boxed them up in terms of just these abstract binary half adders and full adders, but we can build these things just with logical gates to add n-bit numbers up very quickly inside a circuit. And that's it for binary adders.